Time crystals, the material that breaks time. What if I told you a material exists that physicists once swore was impossible? A substance that seems to bend the fundamental laws of time as we know them. This isn't science fiction. It's a real, newly discovered phase of matter called a time crystal. Its structure doesn't just repeat in space, like a diamond, but it repeats in time, oscillating in a rhythm that, theoretically, could go on forever without using any energy. This is the story of a discovery that's forcing us to rethink reality itself. Most of us picture crystals as solid, motionless things. Think quartz or a snowflake. Their beauty lies in a perfectly ordered grid of atoms, a pattern that repeats across all three dimensions of space. They are the very definition of order. A time crystal takes that idea and adds a mind-bending fourth dimension, time. Imagine a clock that could tick forever without a battery. That's the basic idea of a time crystal. Its atoms are in a constant rhythmic state of motion, flipping back and forth, all while being in their absolute lowest energy state. Section 1. The scientific heresy. On the surface, the whole idea sounds like it's breaking the most sacred rules of physics. For centuries, we've understood that things naturally run down and settle. It's a law of the universe called the second law of thermodynamics, which says that disorder or entropy always increases. A hot coffee always gets cold. A spinning top always wobbles to a halt. Everything winds down to a state of rest. So the concept of a material that could move perpetually in its lowest energy state, without any fuel, sounded a lot like a perpetual motion machine, something long ago dismissed as pure fantasy. When Nobel Prize winner Frank Wilczek first cooked up the idea of time crystals in 2012, the scientific community was, to put it mildly, skeptical. He wondered if the way a uniform liquid spontaneously freezes into a patterned crystal could also happen in time. Could a system just decide to start ticking on its own? At first, the answer from other physicists was a hard no. They published papers arguing that any system in its true ground state had to be perfectly still. Any movement would imply there was extra energy to lose. For a moment, it looked like the time crystal was just a cool thought experiment, destined for the cutting room floor. But there was a loophole. The arguments against time crystals all assumed the system was in perfect equilibrium. What about systems that are deliberately kept from settling down? This is where the story pivots from a theoretical no way to a laboratory what if. There's Section 2, the breakthrough moment. The key wasn't to find a time crystal existing peacefully in nature, but to build one. Specifically, what's known as a discrete, or floquet, time crystal. This kind of time crystal gets a periodic nudge from an outside force, like a pulse from a laser. Now you might be thinking, that's cheating. If you push something, of course it's going to move. But here's where it gets weird. The crystal doesn't move with the same rhythm as the push. Imagine pushing a kid on a swing. You push every 2 seconds, and the swing moves back and forth every 2 seconds. Simple enough. But with a time crystal, you might zap it with a laser every 2 seconds, and its atoms would only flip their state every 4 seconds, or every 6. It picks its own, slower rhythm that's completely independent of your push. This quirky, out-of-sync response is the dead giveaway that it's not just following orders, it's a true time crystal. In 2016, this wild idea finally became a reality. 2 different teams, one at the University of Maryland and another at Harvard, managed to create time crystals in their labs. The Maryland team used a chain of 10 ytterbium ions held in an electromagnetic trap, hitting them with laser pulses and watching them flip their spins at a fraction of the laser's frequency. The Harvard team saw a similar effect in densely packed nitrogen vacancy centers inside diamonds. The impossible had officially been done. Today, the go-to playground for making time crystals is a quantum computer. Machines like Google's Sycamore processor are the perfect sandbox, offering an incredibly controlled and isolated environment to line up quantum bits, or qubits, and poke them with precision. In a major experiment, scientists used Sycamore to program 20 qubits to act as a time crystal. They zapped the qubits with a microwave laser to get them ticking and watched as they flipped their spins at exactly half the frequency of the push they were given. The secret sauce that keeps this delicate dance from falling into chaos is a phenomenon called many-body localization. In most systems, the energy from that laser pulse would quickly spread through all the particles, causing them to heat up and lose their special rhythm. But in a many-body localized system, the particles are sort of stuck, prevented from sharing energy with each other. This localization traps the system in its time crystal state, allowing the oscillations to continue without the system heating up and breaking down. This discovery is literally rewriting physics textbooks, showing us that matter can exist in phases far stranger than we ever thought possible. If you're amazed by how science is constantly pushing the boundaries of reality, make sure you subscribe so you don't miss our next trip to the frontiers of what we know. Section 3. What it means for us. So a material that ticks in this bizarre, protected rhythm is a huge scientific deal. But can we actually do anything with it? The answer lies in its incredible stability. While today's time crystals are still delicate and only last for a limited time, the properties that make them so strange are the same ones that could make them revolutionary for technology, especially quantum computing. Quantum computers promise to solve problems that are currently impossible for even our fastest supercomputers. But their biggest weakness is something called decoherence. Qubits, the heart of a quantum computer, are unbelievably fragile. The slightest vibration or change in temperature can mess them up and erase the information they hold. It's the main reason we don't have massive, error-free quantum computers yet. Time crystals might offer a way forward. Because they are naturally tough and resistant to outside nudges, they could be used to build more robust qubits, encoding quantum information into a protected oscillating. Time crystal could create qubits that are much better at ignoring noise, cutting down on errors, and paving the way for more powerful quantum machines. Some scientists think they could even be used to build a new type of quantum memory. Beyond computing, the super-stable ticking of time crystals could lead to ridiculously precise sensors. Think of atomic clocks that are thousands of times more accurate than they are today, or sensors that can detect the absolute tiniest changes in magnetic fields. These ideas are still on the horizon, but the fundamental physics makes time crystals a very exciting candidate for the next generation of precision tech. Section 4. The future is weirder. The world of time crystal research is moving incredibly fast. Just when we've wrapped our heads around the basic idea, scientists are already finding even more exotic versions. For instance, researchers have now created time quasi-crystals. Regular crystals have a pattern that repeats perfectly. Quasi-crystals found in the 80s have an ordered structure that never repeats itself. A time quasi-crystal does the same thing, but in time. Its particles oscillate in an ordered but non-repeating pattern, like a complex musical chord instead of a single, steady beat. Scientists are also working on topological time crystals. In these, the time crystalline behavior is protected by the powerful principles of topology, making the system as a whole even more resistant to errors. While claims of them lasting for exceptionally long periods aren't yet confirmed, recent breakthroughs have shown that these enhanced versions can last significantly longer than the originals, a critical step towards making them truly useful. Conclusion. The discovery of time crystals marks a massive shift in how we see the world. It shows us that at the quantum level, the universe is far stranger and more wonderful than we ever imagined. What was once brushed off as a violation of physical law has now been built and controlled in labs around the world. No, they don't give us free energy or let us build perpetual motion machines. They are non-equilibrium systems that need a nudge to get started. But they do prove that perpetual, ordered motion is possible in the quantum realm, inside a bizarre and beautiful new phase of matter. Time crystals are a reminder that even our most cherished scientific rules are made to be questioned. They live on the absolute bleeding edge of physics, connecting quantum mechanics with our study of materials. The journey of the time crystal, from an impossible idea to a real object, leaves us with one thrilling question. If matter can form a crystal in time, what other impossible things are still out there, just waiting for us to be bold enough to look for them?